Test. Is my microphone okay? Hi, welcome to this week's recitation. And then let's work on this week's problems. For the first problem, we need to make some corrections. First, please change the 6 and 2 to 0. These two terms should be 0. Since the detailed computation is quite tedious, so I will not solve this problem right here. I will just give you a hint and leave it to you. For this problem, you can use the formula for a block triangular matrix. You can just use row or column exchanges. And theorem 4.2.e in the lecture note to help you solve this problem. The second one is much more difficult than the first problem. To show that k and m have the same parity, we will prove that if a product of swap row operations is identity, then the numbers of the swap operations must be even. What I mean is, if the identity matrix can be written as a product of row exchanges, then the number of the row exchanges must be even. Then how to prove that? For simplicity, since to prove this problem, we will use a lot of swap operations. So for simplicity, that's the swap row operation Pij be denoted as Ij. Now, the first lemma is that E1 and E2 be two different swap row operation. Swap now, if E1 moves row K and so if E1 moves the kth row, then there exists some swap operations. Swap F1 and G2 exist such that E2, E1 is equal to G2 F1 where F1 fixes row K, F1 fixes row K, and G2 moves row K. Now, first we try to prove this lemma, and we call this lemma 1. Since we said E1 moves row K, so that's E1 is equal to KA. And because E1 is not equal to E2, then E2 has three possibilities. E2 has one of the forms. The first possibility is that, E2 also moves row K, or E2 moves row A, or E2 moves neither row K and row. The third probability is that E2 doesn't move row K or row A, so we suppose E2 moves the other two rows where K, A, B, and C are distinct integer. Now, if E2 is in this form, then E2 E1 is equal to KB KA, and you can check by yourself. This is equal to KA AB, and this row exchange fixes row K, and this swap row operation moves row K. Then how about the second possibilities? If E2 is in this form, then and it is equal to KB AB, and the third case, if E2 is in this form, then this is equal to KA BC. Since in all the three cases, we can express E1, E2 into some F1, G2, such that F1 fixes row K and G2 moves row K. So this proves lemma 1. This proves lemma 1. Now we need the second lemma. If the identity matrix can be written as a product of n swap row operation, then it can be written as a product of n minus 2 swap row operation. Okay, now let's prove lemma 2. First, we let I be En and so on, E3, E2, E1, where n is greater than or equal to 3, and EI is a swap row operation. Suppose that E1. Now we suppose that E1 moves K. Suppose E1 moves row K. Then if E1 is equal to E2, then this is identity. So if E1 equals to E2, then E2 E1 is identity. So I is equal to En E4 E3, and in this case we are done. We show that we can return I into n-2 swap row operations. But how about E1 is not equal to E2? In this case, we will use lemma 1. Otherwise, lemma 1 gives E1, E2 is equal to sum G2, F1, where F1 fixes row K and G2 moves row K. And now we have I is equal to En E4 E3 G2 F1. Now again, if G2 is equal to E3, then we can cancel these two row operations. Then we can express the identity matrix into n-2 swap row operations. Again, we are done if G2 is equal to E3. Then if G2 is not equal to E3, we'll let E3 G2 equals G3 F2. Since G2 moves row K, so we can apply lemma 1 again and we can return G2 E3 into some F2 G3 where F2 moves row K. F2 fixes row K and G3 moves row K. Where F2 fixes row K and G3 moves row K. Now for this, we have I is equal to En E4 G3 F2 F1. Now if we continue in this way, either we are done at some stage, or we if we finally arrives at a factorization. I is equal to Gn f n-1 and so on. F2, F1. Where F1 to Fn fixes row K. Fixes row K and Gn moves row K. But this is impossible since this is identity. So if Gn moves row K, the kth row will not be at the same place. But this cannot happen. And this proves lemma 2. Okay, with these two lemmas, now we can prove exercise 2. Proof of exercise 2. First, we let P sigma be E1, E2 to EK, and this is equal to E prime 1, E prime 2, and so on to E prime m. Where EI and EJ prime are swap row operations. Then we have here we move this product of row exchanges to this side of the equation. So we have I is equal to E1, E2, and so on to EK, E prime m, E prime m minus 1, and so on to E prime 1. Now we let P equals m plus k. So here we express this identity matrix with P row exchanges. If P is equal to 1, apparently it's impossible. If P is equal to 2, then it is even, and that's what we want. But if P is if P is odd and P is greater than or equal to 3. If P is odd, then by repeating lemma 2, we can represent the identity matrix as one row exchange. Since now we have P row exchanges, by lemma 2, we can express I into P, P minus 2, P minus 4, and so on. And ultimately, it will go to 1. But that's impossible. Which is impossible. So therefore, thus, P is even. P is m plus k, and it's obvious that m plus k and m minus k share the same parity, since n minus k equals m plus k minus 2k. So n minus k is also even. And that's the end of the proof of exercise 2. Okay, now let's go to exercise 3. First, we analyze this problem into 2 cases. The first case is if either one of sigma 4 or sigma 5 is less than or equal to 3. Then, since the metric is in this form, x, 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 and we have 3 by 3, 0 block here. So, if one of sigma 4 and sigma 5 is less than or equal to 3, then A for sigma 4 or A phi sigma 5 must be located in this area. So one of these two terms will be 0. So then obviously A1 sigma 1, A2 sigma 2, A3 sigma 3, A4 sigma 4, A5 sigma 5 is 0. The second case is if both of sigma 4 and sigma 5 is greater than 3. If both sigma 4 and sigma 5 are greater than, again, we need that matrix. I shouldn't erase it. if both sigma 4 and sigma 5 is greater than 3, then A for sigma 4 and A5 sigma 5 is located in this area. Then for A3 sigma 3, you can only choose from here. And if both sigma 4 and sigma 5 are greater than 3, A3 sigma 3 must be 0. Then A3 sigma 3 must be 0. Then A1 sigma 1, A2 sigma 2, A3 sigma 3, A4 sigma 4, A5 sigma 5 is 0. Then by 1 and 2, we can conclude that all of the terms in the summation is 0. Problem 4 and problem 5 are similar, so I will just give you a hint, and I will not do them here. You can use cofactor expansion along the first row. This problem we will use the formula for block triangular matrices. So first we write down this matrix. And now since we want to use the formula for block triangular matrices, we want to make this block a zero matrix. How can we do that? First, we multiply this determinant by a term that is equals to 1. And it's easy to see that the determinant of this matrix is 1, so we can multiply this term right after this term, and the equality still holds. And now we Now we merge these two matrices. And it gives us and this is equal to then here we can use the formula for block triangular matrix. By Fierron. (4.2.e) in the lecture note. It is equal to the determinant of AB times the determinant of I. And this is 1, so it is equal to determinant of AB. Okay, now let's go to exercise 7. For problem 7, similarly, we try to use the formula for block triangular matrices. First, we'll write down this matrix. A, B, C, D. Now let's see how we can eliminate this C. To eliminate this C, we can multiply the first row by, say, multiply this row by C A inverse, and then add and then add it to the second row. So we have and now we multiply this matrix by this matrix. Minus C A inverse I A B C D, and it is equal to the determinant of the matrix A B 0 D minus C A inverse B. So again, by the formula for block triangular matrix, we have determinant A times determinant of D minus C A inverse B. If a problem asks you to show that something, if and only if something, make sure you show the works of both directions. That means if you are required to show that P, if and only if Q, then you need to show that P implies Q, and Q implies P. For the first direction in this problem, it's pretty easy, so we will leave it to you. We will not do it here. We will. Then, for this direction, instead of showing that A's cofactor matrix is invertible, then A is invertible, we will show that if A is not invertible, then the cofactor matrix of A is not invertible. Here, we will show that if A is not invertible, then A's cofactor matrix is also not invertible. Now, we analyze this problem in two cases. First, if A is a zero matrix, then apparently A's cofactor matrix is zero. So A's cofactor matrix is not invertible. Then for the second case, it looks like I need to use another blackboard. For the second case, if A is not equal to a zero matrix, then by theorem 4.2.c in the textbook, we have since we assume that A is not invertible, so determinant of A is zero. So this is a zero matrix. Then it basically tells us that the system, the linear system, has non-trivial solution. Since A is now a zero matrix, so this linear system has non-trivial solution. If a linear system has non-trivial solutions, then the rows of this matrix form a linearly dependent set. Oh, sorry, the columns. So the columns of the transpose of the cofactor matrix of A form a linearly dependent set. Linearly dependent set. So if we take the transpose of this matrix, the rows of A's cofactor matrix form also form a linearly dependent set. Then, if the rows of a square matrix form a linearly dependent set, then its determinant is 0. So, determinant of A's cofactor matrix is 0. You can check theorem 4.1.4. 1.4. Therefore, A's cofactor matrix is not invertible. And we are done. For exercise 9, you can just use theorem 4.2.c in the lecture notes and use the previous exercise. Okay, first we know that the determinant of A's cofactor matrix is 3. Then by previous 2 problems and exercise 9, we can know that A is invertible and determinant of A is equal to the cube root of 3. Then by theorem 4.2.c, the transpose of A's cofactor matrix multiplied by A is equal to the identity matrix multiplied by the determinant of A. Now, we can see this as a linear system, and A is its solution. So A is the solution to the linear system. We have solved this kind of linear system many times in previous homework, so I believe you know how to find A. So the rest will leave to you, and we will not do the calculation here. So please find A by yourself. We leave the rest to you. Okay, the last exercise is an easy exercise, so I will just give you a hint and leave it to you. Use theorem. If you review this theorem and this exercise, then I believe you know how to work out this problem. Then we are kind of done here. Is there any questions? Okay, then if there's no other questions, then that's this recitation. I will see you next week.